Okay, so what I'd like to talk about right now is mean value theorem and Rolle's theorem and how they apply, when you can use them, all of that. So I'm actually going to start by looking at Rolle's theorem, and I'm going to start by drawing it. So forgive my artistic work here, but we're going to say if we're looking at some curve, I'll just draw a parabola here. It opens down, and we're going to look at 2 points on this parabola. So let's say this point right here, which I'll say has an x value of a. We'll just call this y value f of a. And then on the same horizontal level here, an x value of b. And that is the same y value, so we're going to say equals f of b. Okay, those are the same y values. So if you found the slope between these two given points, or the average rate of change, I would hope we can see quite easily that that is 0, because that's a horizontal line. Horizontal line is a slope of 0. And what Rolle's theorem says, and this is a really, really important part of Rolle's theorem, is that if we are continuous, and within that window, if we are differentiable, then we can go ahead and apply this theorem. And basically, you've heard before, I'm sure, what goes up must come down. Well, that's because we're trying to leave a certain y value, increase or decrease out of it, and then we need to at some point then turn around to get back down to the same y value where we started, or to get up. So if my parabola was exactly opposite of that, here's my y value where I'm starting. Again, if I'm continuous and I'm decreasing, then at some point I'm going to need to turn around and increase to get to that same y value level. Okay? So what I'm going to show is that there is a guaranteed existence of a horizontal tangent line in between A and B, and we call that x value C. And so C will be in between A and B, and its slope of its tangent line, so that f prime of C, if you will be 0. And coincidentally, that's the same slope that if you found between A and B, you would get there. So let's see this in action with number 1. So the first things first that we did not say, that is a condition to even apply Rolle's theorem, which is why it often says determine if Rolle's theorem can be applied or not, is that you have to be continuous and you have to be differentiable. I don't know what that was going to be. All right, now, again, I don't need to be continuous and differentiable forever. I just need to be continuous and differentiable in that given window, and I was given the window from 1 to 4 for x, and I think we can all agree that this parabola is continuous and differentiable everywhere, but I'm really only concerned with the window from 1 to 4, that interval. So I did find f prime of x, right? This is my instantaneous rate of change, or my instantaneous slope, slope of my tangent line for any x value, all of those things. And I set that equal to 0. And what I'd like to show right now is that that actually is the slope. If you found the average rate of change from 1 to 4, that is the same slope. So, for example, f of 1 and f of 4, or we can write them as points, 1 comma something and 4 comma something, and then we can take those 2 points and find the slope. And that's the slope of a secant line because it goes through twice. So if I put a 1 and substitute that in for x into my function, you get 1 minus 5 plus 4, negative 4 plus 4 is 0. So I can write it as a point or in the function notation. And then if I substitute in a 4 for x, I get 16 minus 20 plus 4. Negative 4 plus 4 is 0 again. And so the 0 is not as important as the fact that they are the same, because what happens is when I find my slope here and I do y2 minus y1 over x2 minus x1, or change in y over change in x, I should easily be able to see that that's 0 over 3 or 0. So here I'm seeing that the average rate of change between these 2 points is 0. And that's what Rolle's theorem is basically saying. So they're guaranteeing you the existence of that horizontal tangent line if you're continuous and differentiable between there, so long as the y value, right, of your 2 points is the same. Okay, so that is Rolle's theorem. Now, mean value theorem is actually a little bit more, a little bit less specific, or a little bit more generalized actually, because they're not always having a slope of 0, but it's the exact same idea. So I will draw it. And again, I'm just going to draw some downward facing parabola. I'll identify 2 points on here, A, f of A. And now when you draw these, the f of A is not necessarily equal to the f of B. Okay, so if I look at the secant line between these, or if I just connect these, I can find the slope between these 2 points, and I know I only drew the segment, but I can find the slope, or the average rate of change between A and B. So the slope between A and B is going to be your f of B minus f of A all over B minus A, right? Your average rate of change. Now in this case, it might look like, I don't know, negative half or something, because it is a decreasing line. And so mean value theorem is going to guarantee the existence of some parallel tangent line, maybe about right here. That looks pretty good for me. So what they're saying is this secant line is parallel to that tangent line. And again, we're saying that that point of tangency, or at x equals c, is going to be between A and B. Now the same conversation exists if you are not continuous and not differentiable. You cannot make any of these statements. So that's all written up above in written form. I just wanted you to see what it looks like in graphical form. And we're going to say that this slope, or average rate of change, is equal to this instantaneous rate of change, or f prime of c. So looking at this one in algebraic form, if you will, so determine if mean value theorem can even be applied. Well, that's because when you look at your function over this interval, right, because again, I'm only concerned, between -1 and 1, I want to make sure that I'm two things. I want to make sure that I am continuous, and I want to make sure that I'm differentiable. So, am I continuous? Yes, because I'm a third degree polynomial, right? I'm actually continuous everywhere, but I have no domain restrictions, certainly not between -1 and 1. And am I differentiable? Yes. Now we can be continuous and not be differentiable. We talked about this before. For example, the vertex of the absolute value, any sharp turn, cusp, or kink in a function, you are continuous and your function does exist there, but you are actually not differentiable there. And also the beginning of the square root curve, that you are not differentiable. So what we did here was we found the slope, or the average rate of change between the 2 points. Again, since you were given this -1 to 1, the -1 is my first x value, the 1 is my second x value. You can find the y values, then you can find the slope. That is an average rate of change. So there's my slope of -1, and I set that equal to the instantaneous rate of change, or that instantaneous slope, which is my first derivative. And so then this was a quadratic equation, so I set it equal to 0 and solved it. I did get two answers, And remember, you want the one that's inside your interval. So you find the values of C in the open interval AB. So you want it inside of -1 to 1. And so the one that's inside the interval is -1/3. And so that is my C value. So at C, or x equals -1/3, I'm going to have a slope of -1, which was what my secant slope was between those 2 points as well. And so if I wanted to kind of summarize this for you, both of these theorems sort of do the same thing, assuming that you are continuous and assuming that you are differentiable, or proving that you are these things. You are finding your first derivative, which is your instantaneous rate of change, and you are setting that equal to your average rate of change. So here's instantaneous. And this is all average. I won't be lazy, I'll write it all out. Okay, it just so happens that in Rolle's theorem, I like to think of it as with an O, Rolle's theorem, that your slope or average rate of change between the 2 points will turn out to be a 0, but mean value theorem, it will be some other number. And so you can see it up there in written form. You can also see that Rolle's theorem can be used to solve mean value theorem, but hopefully that helps you understand it a little bit more.